Hello student, in this lecture I will discuss the fundamental of Bode plot technique. Okay, so I am going to discuss the fundamental of Bode plot technique. So basically Bode plot consists of two subplots that plots are magnitude plot and phase plot. So Bode plot basically consists of two subplots, that means magnitude plot and phase plot. By comparing these two plots, we are going to get the Bode plot. So coming to magnitude plot and phase plot. Okay, so both this plot contains the similar x-axis. That means x-axis the angular frequency, where angular frequency is equivalent to omega. These two plots differ in y-axis. Okay, for magnitude plot, the y-axis is the magnitude of open loop transfer function, and if you know open loop transfer function, the magnitude of the open loop transfer function can be obtained by taking modulus and 20 log. Okay, so this is the magnitude m 20 log. So this is the magnitude, that means this. So this is the magnitude m equal to 20 log g j omega h j omega of open loop transfer function. Okay. Finally, magnitude, which is nothing y-axis of our magnitude plot, is equivalent to 20 log g j omega h j omega. Okay. So this omega we need to consider as x-axis. That means with reference to omega we need to plot of the magnitude. By changing omega we need to calculate the magnitude. Now by plotting the value with respect to omega, that means angular frequency, we are going to get our magnitude plot. Now coming to the phase plot part. Okay. So as I told, y-axis is different for magnitude plot and phase plot. So for phase plot, y-axis is equivalent to phase angle of open loop transfer function or closed loop transfer function, whatever you have taken. Okay. So here phi, phase angle phi equal to angle of gj omega and gj omega and hj omega. Okay. Now coming to different basic Bode plot. Okay. So for example, if we are having constant, so Bode plot. So here I have discussed Bode plot basically consists of two plot. One is magnitude plot and another one is phase plot. So magnitude plot is defined m equal to 20 log g j omega into h j omega. So by varying omega we plot the magnitude of our open loop or closed loop transfer function, and phase plot is phi equal to angle of g j omega and h j omega. So in this case here also we plot the phase angle of our open loop or closed loop transfer function by varying omega. Okay. Now we are going to discuss the different part of Bode plot. Okay. See here, this table, the following table shows the slope, magnitude and the phase angle values of the terms present in the open loop transfer function. Okay, so this data is basically useful while drawing the Bode plots. Okay. So now I will discuss this constant term 0 at origin and 0 at n number of zeros as origin 1 by 1. Okay. So see the table. Now first we take the constant part. Okay. So see here we consider the open loop transfer function GSHS equal to K. So if you calculate the magnitude of this constant part, then the magnitude m equal to 20 log k dV. The base of this log is 10, okay, and phase angle is 0 degree. Okay, now see, if k equal to 1, put the value of k in magnitude part. So see, if k equal to 1, then our magnitude is 0 dB. And if k greater than 1, then magnitude will be positive. See, if k greater than 1, then magnitude is positive, and if k less than 1, then the magnitude will be negative. Okay, so now put the value in the magnitude plot. Okay, so if we put the value in this graph, that means in log paper, then our graph will be like this. So see here, if k equal to 1, then our magnitude is 0 dB, that means this. Okay, if k greater than 1, then magnitude shift upward, and if k less than 1, then magnitude shift downward. Okay, and second graph represent the phase plot. Okay, so phase is always constant, that means 0 degree for constant part. Okay, so this is show the straight line. Okay, so see, the magnitude plot is a horizontal line which is independent of frequency. The 0 dB line itself is the magnitude plot when the value of k is 1. For the positive values of k, the horizontal line will shift 20 log k dB above the 0 dB line, and for the negative values of k, the horizontal line will shift 20 log k dB below the 0 dB line. The 0 degrees line itself is the phase plot for all the positive values of k. Okay. Now, here we consider the open loop transfer function GSHS equal to S. Okay, so if our open loop transfer function GSHS equal to S, that means GSHS equal to S means in this case our 0 lie in the origin. Okay, so here we draw the magnitude, we know the magnitude. So if we put this S equal to j omega, and after this we calculate the magnitude, then the magnitude is m equal to 20 log 10 omega dV. Okay, and phase angle is 90 degree. Okay, phase angle is 90 degree. So see, at omega equal to 0.1, if we put omega equal to 0.1 radian per second, then the magnitude is minus 20 dB. Okay, and if omega equal to 1 radian per second, then the magnitude is 0 dB, and if omega equal to 10 radian per second, then the magnitude is 20 dB. Okay, now we put the value in this graph. Okay, so see, if omega equal to 0.1, then our magnitude is minus 20 dB, that means this one here. If omega equal to 1, then our magnitude will be 0 dB, and if omega equal to 10, then our magnitude is plus 20 dB. Okay, so now we connect this to 3 point. Okay, so this is our graph. Okay, so and this is our phase plot. Okay, so phase is always 90 degree if our open loop transfer function is S. Okay, so see, the magnitude plot is a line which is having a slope 20 dB per decade. Okay, this line started at omega equal to 0.1 radian per second, having a magnitude of minus 20 dB, and it continues on the same slope.